In presentation 16, cupellation was discussed. It is the first phase of the refinement of gold from the lead bead obtained from the fusion process. Now that you have the door bead, what next? You still need to extract the silver and other metals, usually the PGM group of metals, if any present. This process is referred to as parting. Inquartation may be necessary. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. What is being done during parting is the separation of the gold and platinum group metals from the door bead. This is accomplished by the addition of nitric acid. Sulfuric acid may also be used, however, it is mainly used when parting large quantities of bullion. Nitric acid is the most commonly used solution. Since gold is a noble metal, it resists the reaction of the acid and does not ionize into the solution. As mentioned in presentation 16, to conduct a successful parting, the ratio of 3 parts silver to 1 part gold is required in the door bead. Many textbooks will tell you that a ratio of between 4 and 6 parts silver to 1 part gold is best. Nitric cannot be used successfully if the ratio is less than 3 to 1. With a ratio of 3 to 1, it will require a stronger nitric solution with a longer continued heating to fully separate the silver from the bead. With larger concentrations of silver in the bead, special precautions must be taken. With concentrations of 6 to 1 or greater, the bead will break up into smaller particles. The parting process must be manipulated in a way that results in the particles being left in a single mass. The strength of the nitric acid solution is dependent on the silver to gold ratios. The lower the ratio, the stronger the solution that may be used without having the bead break up into smaller particles. It is best to conduct an initial parting without inquartation, which will be explained in an up-and-coming slide. This is done to estimate the amount of silver in the bead. To start, a hot plate of some type will be needed. It is used to speed up the reaction of the nitric acid. Ceramic or glass parting cups, having a capacity of 10 to 12 milliliters, are necessary. The nitric acid solution should be of a high concentration. It will be cheaper in the long run when you dilute it to what is required. The silver is used for inquartation if required. It must be lead-free. For the inquartation process, silver-free lead foil will be needed, or Herman inquarts may be used. A hammer and an anvil will also be required. The anvil and hammers that are used for this process are designed to be contaminant-free. Once the bead is removed from the cupel, it is vital that you clean it. You will then take a hammer and flatten it out on an anvil. This increases the surface area, which enhances the acidic reaction for a more complete parting. The anvil and hammer should be made from a material that will not leave any iron or other particles that may contaminate the bead. Once flattened, it must be weighed in order to estimate the silver content. Now your bead should be ready to be placed into the parting cups. The cups must be free of dust, they must be clean, and they must be dry. The cups are then filled with nitric acid. The solution is made by using 1 part of concentrated acid to 6 parts of distilled water. They are then placed on the hot plate and heated. It is important to make sure that the solution does not boil. If this happens, your gold bead will or may turn to powder. Continue heating until all the reaction stops. As the silver dissolves, bubbles of nitrous oxide will be given off. When all the reaction stops, top up with dilute nitric acid. This solution should be made of 1 part acid to 1 part distilled water. Continue heating for another 10 to 20 minutes. Once the parting has been completed, decant the solution into another beaker, being careful not to lose any residue. You do not want to lose any gold which may have become finely divided. Do not discard the solution. It is a silver nitrate solution that can be processed later and reused. Wash and decant the cups at least 3 times, removing as much water as possible without loss of residue. When washing, ensure that the water stream is a fine stream. When adding the water, pour it down the sides of the cups to avoid direct stream contact with the bead or fine gold powder. You do not want to impact the bead. This may cause it to break apart. Set the cups containing the beads and residue back onto the hot plate. Using a lower temperature, allow the cups and material to dry using a slow evaporation process. The intent is to reduce the possibility of sputtering of the last few drops of water. That may break up the gold bead, which could throw some gold out of the cup. After which, anneal the beads, which will be explained in this presentation. Once annealed, weigh the beads. The difference in weight will be the amount of silver that was contained in the door bead. This can be used for the inquartation process if required. The intent in regards to parting is to end up with a gold bead that is at least 3/9 pure. More than that requires additional processes, which is not covered in this series. After parting, if your beads are not that bright, beautiful, shining yellow color throughout, but are a little on the light colored side, there will still be some silver alloyed in the bead. Inquartation will be necessary. As mentioned during parting, silver nitrate will be the product that is decanted. However, if the parting has not been fully completed, some silver nitrate will still be present. This will show up as dark spotted areas on the bead, as well as a stain on the parting cup. Gold is slightly soluble in highly concentrated nitric acid. Loss does occur if acid solution is highly concentrated. Never use concentrated nitric acid for parting. During the parting process, if the telltale nitrous oxide bubbles do not appear, and the bead may or may not turn black, it means that the silver content in the bead was too low, and there was no reaction with the nitric acid. Parting will not be complete, and inquartation will be necessary. Now, if that bead turns to a powder, that is, it disintegrates, the silver content was way too high, or the solution during parting was allowed to boil. Caution during decanting is a must. Some of the finer gold may be poured out and lost in the silver nitrate solution. The graphic depicts the removal of the silver from a bead. The silver atoms and the gold atoms are randomly displaced throughout the bead. As the silver is dissolved, it leaves microscopic holes throughout the remaining bead. The bead will not have a solid, defined structure. It is said to be amorphous. This is the reason why the bead may break down into a powder or just simply break up. This is the reason why the bead is annealed. That process will be discussed later in this presentation. It is important to estimate the amount of silver in the bead. This is usually done by conducting a preliminary parting without inquartation. This is done by weighing the door bead prior to parting and then weighing after the parting. The weight in silver is estimated. It is the difference between the two weights. Now, using this information, the ratio of silver to gold can thus be estimated. Any gold concentration in a bead that is greater than 25%, or 1/4 the weight of the bead, silver will not part. Silver must be added. Any gold concentration that is less than 1/6, or 16%, the silver concentration is much higher, and the bead will disintegrate. The silver concentration must be adjusted to give a ratio of silver to gold between 3 and 6 to 1. The aim is usually 4 or 5 parts silver to 1 part gold for best results. If the preliminary parting suggests that the silver to gold ratio is 1 to 1, and you're looking for a 4 to 1 ratio, it can be achieved by adding 1.5 times the bead's silver weight in silver. If it is less than 1.1, then it is 3 times the bead's silver weight in silver. As shown in the example, if the bead weight was 1.3 grams at the start and it was estimated to have a ratio of 1.1, we would add 0.98 grams of silver for the inquartation. Now that you know the ratio and have weighed out the appropriate amount of silver, take the bead and the silver and wrap it up in a suitable amount of silver-free test lead foil, as shown in the right lower left of the slide. Then recompel. The new bead obtained will have or should have the right ratio of silver to gold. This new bead should part easily and completely. Prior to parting, the bead should be weighed. After parting, the bead should also be weighed. The difference will be the amount of silver parted. The difference between the silver parted and the silver added should be the amount of silver that was in the bead to start with. Silver comes in 3 forms: powder, wire, and Hermann inquarts. The powder and the wire forms must be lead-free. Most are 4/9 pure. Hermann inquarts are pieces of test lead alloyed with silver. These come in different concentrations and may be used along with the test lead foil for simplicity. However, wire is more common, and so is powder. The most commonly used is the wire. Now that you have that amorphous bead, it has to be annealed. This should be the final step if all goes well. Annealing will transform that porous bead and any fine particles into one solid mass. It will also develop that nice shiny yellow color. On inspection, any impurities will be easily and readily seen. Annealing also burns off any foreign matter that may have contaminated the parting cup. That dry parting cup containing the bead and any fine dislodged bead material is placed into a furnace and the temperature brought up to 800 degrees centigrade. It is held there for 5 minutes or so at that temperature, removed and then cooled. A Bunsen burner may also be used. Place the parting cup on top of the burner utilizing the correct stand until the bottom of the cup turns to a bright red color. The temperature must be between 700 and 800 degrees centigrade and held at that temperature for at least 5 minutes. Remove, cool, inspect, and weigh. The bead should be at least 3/9 pure. A lot of videos will present annealing using a torch. This is not really recommended. The pressure produced by the torch, which is directed directly onto the bead, may cause airborne particles to be impregnated into the bead, thereby contaminating it. If not using a furnace, a Bunsen burner is a safer method for the annealing of those parted beads. There are other considerations that you should be aware of. Silver-rich beads that have a weight greater than 2 milligrams may and will disintegrate. When this happens, not all is lost. Those fine black particles of gold may be collected by adding a drop or two of diluted hydrochloric acid into the parting solution. The parting solution, when parting reaction is complete, the resulting product is actually a silver nitrate solution. Another type of chloride solution, such as sodium chloride, may be used. The silver chloride will actually precipitate and collect those fine gold particles. They can then be filtered off and the paper ignited, scorified with lead, then compelled. The resulting bead may then be parted. The practice of flattening the bead is done to create a larger surface area for the nitric acid to complete the parting process more efficiently. Any bead that weighs up to 500 milligrams can be flattened out using a hammer and an anvil, one that will not contaminate the bead. Make sure that no slag or other forms of contamination will be hammered into the bead. Any beads greater than 500 milligrams will need to be rolled thin using a jeweler's press. Annealing will be required intermittently throughout this process. Once thin enough, they should be rolled into a cornet. For the parting process, parting cups are most commonly used. However, porcelain crucibles can be used satisfactorily as well. Nitric acid is mostly used as the solvent, but sulfuric acid is used for large-scale parting. The important thing to remember is to use distilled water for dilution, washing, and so on. The water must be chloride-free. The chloride will contaminate the gold with silver chloride, and if the chloride concentration is large enough, it will aid in the dissolution of some of the gold. The strength of the nitric acid will determine the ionization rate of the silver. However, it will also result in a greater chance of the gold disintegrating. Even though gold is a noble metal, it is to some extent soluble in hot concentrated nitric acid. This is the reason why the nitric acid is diluted. The standard practice is to use a diluted concentration of 1 part acid to 6 parts of distilled water. Then heat to or just below the boiling point for 20 to 30 minutes. The boiling point of nitric acid is 83 degrees centigrade. When the reaction stops, then topping up the parting cups with a nitric solution having a 1-to-1 concentration and heating for another 10 to 20 minutes should result in a good bead. The point is to not let the solution come to boil. The mechanical action of the boiling solution against the bead can and may cause it to disintegrate. Do not boil. When decanting or washing, use a wash bottle with a large aperture nozzle which provides a gentler stream. Always add wash water to the parting cups by streaming the water down the sides of the cups. This prevents a direct stream from being applied directly to the bead, which in turn will cause it to break apart. Remember that the bead is amorphous. To ensure that all the silver is washed out of the cup and off of the bead, wash and decant at least 3 times. Do not discard any of the decanted solution. This end product solution is silver nitrate, and the silver chloride can be precipitated and collected at a later date. When drying on the hot plate, do so with a lower temperature. You want to ensure that the sputtering of the last drops of liquid does not occur. A slower evaporation will ensure that there will be no losses due to sputtering, as the process of sputtering can and does dislodge the fragments from the bead and can eject them out of the parting cup. Once dried, cooled, and annealed, inspect the beads for contamination as well as the parting cup. Any silver left on the bead will show up as dark spots or a stain on the parting cup. This presentation, Presentation 17, is the final presentation of this series on the fine art of fire. It would not be complete without showing the reference material used in this series. From the top, the National Audubon Field Guide to Rocks and Minerals is a good source for the chemical makeup of most of the ore material that you may encounter. The Textbook of Fire Assay by Bugbee, The Sampling and Assay of Precious Metals by Smith, The Textbook of Assaying by Behringer, Chemical Fundamentals by Gill and Blackwell, The Manual on Fire Assaying by Hafty, Riley, and Goss are all good sources for processes and procedures as well as chemical reactions. For lab procedures, Lab Instruction by Morley and the Crucible Handbook by Schwartz, White, and Curtis was good references for laboratory material and process. The last is the British Columbia's Institute of Technology. The Mineral Assayers Training Program conducted by the School of Energy and implemented by Elaine Wu, Program Coordinator and Instructor, was an invaluable resource. References taken from the Fire Assay module. For anyone that is connected to the mining industry in any capacity that would like to know more about mineral assay or wish to become an assayer, I highly recommend the BCIT program. It is offered as a distance education program for the first 4 modules. The 5th module must be taken at the campus. This presentation on parting is the last in this series. I have mentioned that the fire assay process was the most economical and accurate method used for the pre-collection, collection, and refinement of the precious and noble metals. This series focused on the gold and silver assays. It is designed for the small-scale miner or prospector, not for the laboratory technician or professional assayer. Therefore, the process of collecting and the refining of the platinum group metals was omitted and is beyond the scope of this education series, as those processes require a wet, dry methodology and more advanced equipment. The entire 17 presentations put together could be considered as an introductory course in fire assay. If you like this final presentation, or know of someone who may benefit from this information, please give it a like, a thumbs up, and a share. It's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.